Bam! Mr. Tarrou. In this video, we're going to do 3 examples involving special trig limits, something that you should have started exploring in the previous section where you and my students were analyzing limits both graphically and numerically. T-tables. Kind of monotonous and time-sucking. So we have the limit as x approaches 0 of the sine of x over x. Now, we are currently going to be in this section working through solving limits analytically, factoring the numerator and denominator and see if we can get some factors to cancel. So we find a function that agrees with the original function everywhere but one point, or maybe rationalizing the numerator. Well, we're going to be algebraically manipulating these expressions to get these expressions to as closely as we can, or exactly, match these patterns that are in our limit statements, and specifically as x approaches 0. The answers we're going to have here in a minute don't apply for x approaching any other number, or infinity, or negative infinity for that matter. In the description below, you'll find timestamps to jump ahead to any one of these 3 examples. The last one is quite a challenge, and links to any one of my other 700 plus math videos I've made to this date. So these examples, or these limits we're going to use through the video, you are not going to arrive at the real limit of either one of these without either looking at a graph or doing a table of values. So we have here the y is equal to sine of x over x is a function mostly due to the fact that it's got some division of x, but it's got some work with sine of x in it, oscillates along the x-axis asymptotically, and that oscillation increases in amplitude until you get to x equals 0, and then there is a hole, and then the graph kind of settles down and starts to oscillate back towards closer and closer through each oscillation. That amplitude decreases and it approaches the horizontal line y equals 0, or the x-axis. Which is kind of interesting because up until now, especially if you're just coming into calculus, you might be all used to, we all are kind of, is like when you have that factor in the denominator that creates that division of 0, and it's a factor that doesn't cancel, that would be a location of a vertical asymptote. But that's only true for rational functions where the numerator and denominator are both polynomials. Here we have some trig functions going on and things get a little bit more interesting, a little bit more complicated. Y is equal to 1 minus cosine of x over x. Hopefully you did observe this in your previous calculus assignment, but that also is going to have an oscillation where it increases in amplitude. It passes through 0, 0, and we have a hole there because you can't divide by 0. And we have this function which is even, symmetric to the y-axis, and this function, it's not drawn all that super well, and there's no scale on it, which is horrible, but it's symmetric to the origin. So the limit as x approaches 0 of sine of x over x is equal to 1. And this is a two-sided limit, and we're approaching the value of 1 from both the left and the right-hand side. The limit as x approaches 0, a two-sided limit of 1 minus cosine of x over x, is equal to 0. We're approaching 0 as we come in on the left-hand side, we're approaching 0 from the bottom, and as we come in from the right, we're approaching 0 from above, but we're still approaching 0 from both sides for that two-sided limit to exist. Let's get on to our 3 examples. So for example number 1, we have got the limit as x approaches 0 of 1 minus the cosine of 2x over 5x. Now, as you start into working with these problems, to use one of these limit statements, you have to make this expression inside this limit statement, again, specifically just for x approaching 0. You need to get an exact match. Now, but when I say an exact match, I don't mean that the 2x and 5x both need to become a singular x. Variables represent unknown quantities. That quantity may be a number, or it may be a monomial, or it may be a trinomial, or anything. It's just an empty place to put something. So don't think of this as the limit as x approaches 0 of 1 minus cosine of x over x. Think about it as 1 minus cosine of something over something. As long as these two expressions are the same, this limit is going to be 0, and this limit here, the top limit is going to be 1. So can I get the coefficient of this x, which is 2, and the coefficient of this x, which is 5, to be the same? Well, don't forget that what do you put into a trig function? Of course, you put in a measure of an angle. And it's very, there's a lot of math involved in coming up with an equivalent trig expressions where the angle size is different. Think about the sum and difference, double angle and half angle identities, power reducing formulas, all those identities that you learned in trig last year, in pre-calculus last year, that allowed you to work with different measurements of angles within those cosine or those trig functions. So this 2 is going to stay there, and that's not going to be easily changed, but we can work with the 5 quite easily. We're going to start off by working with this property of a limit, which is to say that the limit as x approaches c of some constant multiplied to a function, you're going to be able to just move that constant multiple on that function out and say that that's equal to b times the limit as x approaches c of f of x. So we're going to take that division of 5, or that multiple of 1/5, out and get one-fifth times the limit as x approaches 0 of 1 minus the cosine of 2x over just now simply a singular x. Well, if my x inside the trig function is a double angle, if you will, or has a coefficient of 2, I need to introduce a coefficient of 2 in front of the x, so I get that 1 minus cosine of something over the same something. I want to multiply this. Basically, right now we have sort of like two factors, if you will. I want to multiply this by x over, no, not, I'm thinking of the next question. I want to multiply by 2 over 2. Just gave that away, darn it. 2 over 2, maybe I'll edit that out. So I'm going to multiply all of this by a version of 1. That's going to change the way it looks, but not change its value. And then I'm going to bring that multiple of 1/2, if you will, or that multiple of 2 in the denominator, and bring that into the parentheses, and ultimately have a 2 times 1/5 times the limit as x approaches 0 of 1 minus cosine of 2x something over that same something of 2x in the denominator, and that is equal to 0. So now we've got 2/5 times 0 is 0, and our first example is done. Second example coming up right now. For our second example, we have the limit as x approaches 0 of sine of x squared over x, and this is probably how you would see something like this written in your book, but I like to emphasize the measure of that angle that's going into a trig function. And by the way, about that, and well, you would have probably already seen this in your previous section of homework, but we never work with trig functions in calculus unless the measure of rotation is in radians. It's because it's a radian is the ratio of how far around the circle you've gotten, its arc length, if you will, divided by the radius of that circle. It's a division of two lengths, thus there is no unit of measure for radians, and somehow that made the derivation of all the derivative and integration rules in calculus easier. Well, I kind of, let's see here. In the statement here, it's obviously almost like our first one, and where we got an answer of the limit as x approaches 0 of sine of x over x is 1. If I can get that something that's in the denominator, which is just simply x, to match what's inside the sine function, which is an x squared, I'm going to be good to go. You know what I'm going to do? I'm going to multiply this fraction by, again, a version of 1. I'm going to multiply by x over x. Now when I do that, where I have the limit as x approaches 0 of x over x times sine of x squared over x. Of course, I can bring these two factors together in the denominator and have the limit as x approaches 0 of x times the sine of x squared all over x squared. Now, this is an exact match of what we have as a formula we memorized and hopefully again saw in the last section. The limit as x approaches 0 of the sine of something over that same something is equal to 1. So the limit as x approaches 0, oh, and properties of limits. When you're taking a limit of factors, you can do the limit of each of those factors. That's actually what I'm doing, the limit of each of those factors separately, and then multiplying the answers together. So we have the limit as x approaches 0 of x times the limit as x approaches 0 of sine of x squared over x squared. Our first product, our first limit is going to come out to be 0 times 1, which of course, again, gives an answer of 0. I promise the third example is not going to come out to 0 yet again. So this third example coming up right now. For our last example, we have once again the limit as x approaches 0 of the cosine of x minus 1 over 3x squared. Now, I set up these notes to go over them with you in the video, but I want to look at this last example. It's a pretty tough one, and kind of maybe think of it as potentially you might as a student, which is to say cosine of x minus 1 over some factor of x. Maybe I need to, from this expression, get 1 minus cosine of x over x to show up. Let's see what happens with that. We're going to, like the previous one, maybe pull some factors apart and see if we can't make that show up. The limit as x approaches 0, let's go ahead and take that division of 3 sort of like a little bit away from the fraction and write that as a multiplication of 1/3. If I have a cosine of x minus 1 over x squared, if I have an x squared in the denominator, I need an x squared going into the cosine function, but it is this up here in the numerator, that x is inside the math operation of cosine, not easily changed. So how about we get a singular factor of x down here in the denominator? We're not going to just let one of those x's go away, but we're going to pull it apart and write that as 1 over x. And then we have times cosine of x minus 1 over now just x. Okay, so you might be looking here and thinking, oh, it's the limit as x approaches 0 of cosine of x minus 1 over x. That's close enough. And by the way, this comes out to be 0 anyway, so it must not matter what order the subtraction is. Yes, it does. It definitely does. You need to get these patterns to be an exact match before you go off and try and apply or use with substitution the answers to one of these limits. So we need to change the order of that subtraction. Well, 5 minus 3 is 2. 3 minus 5 is negative 2. We're going to change the order of that subtraction by factoring a negative 1 out of the numerator. So we have the limit as x approaches 0 of negative 1/3 times 1 over x times 1 minus cosine of x over x. So everything seems to be going really well now. The limit as x approaches 0 of negative 1/3 is negative 1/3, and you might jump to this conclusion, and I probably have done this a couple of times in class, the limit as x approaches 0 of 1 over x. Well, a 1 over an ever decreasing denominator, like 1 over 1/10, 1 over 100, 1 over 1,000, the answer just keeps getting bigger and bigger and bigger, and the answer is infinity. Well, that's not really right here. Since we're really delving into trying to develop a deep understanding of limits, this is the limit as x approaches 0. There's no plus or minus here. This is a two-sided limit. And for a two-sided limit to exist, both the left and the right-hand limits have to be equal. Well, y is equal to 1 over x is a function that looks like this. as you approach 0 from the left, you're going down to negative infinity, and when you approach 0 from the right, you're going up to positive infinity. So actually, the answer to the second factor does not exist. By the way, if you did think that the answer was infinity, you still have a problem, because the limit as x approaches 0 of 1 minus cosine of x over x is 0, and 0 times infinity or vice versa, that is a form of indeterminate, which means that the limit may exist, it may not, we don't know. But really, the answer to this limit as x approaches 0 of 1 over x, approaching 0 from both the left and the right, is not infinity. If it were approaching just from the right, if there was a little plus sign here, infinity would be okay, but not here. So we tried something, we got some techniques and ideas that we have explored so far, will be useful in other problems. It just isn't here. So let's try again. That's how math is. Not everything comes out super duper easy the first time. To be honest, this is the second time recording this video, because the first time I messed up the sound. So not everything is easy, but we're going to keep fighting, we're going to keep working, and we're going to get it right now. So if this second limit sort of identity, if you will, value is not helping, not getting us into a direction that we want, can we work with this limit as x approaches 0 of sine of x over x? This is a pretty tough question. Can we get a sine function to show up out of this expression? Have we studied anything in pre-calculus or trig that related sine and cosine together in a nice, almost direct relationship? Well, not in terms of degrees of 1, exponents of 1, but we do have this Pythagorean identity, the sine of squared theta plus cosine squared theta is equal to 1. Thus, sine squared theta is equal to 1 minus cosine squared theta. 1 minus cosine squared theta, difference of squares. I've got a cosine of x minus 1. If I multiply this expression by a form of 1 that gets a difference of squares to show up, I'm quite a bit close to getting to a situation where I can use this first limit statement. So we're going to multiply. Here comes all those trig proofs you did in pre-calculus that I hope you liked. We're going to multiply by the cosine of x plus 1 in the numerator and denominator. And when we do that, we're going to have the limit as x approaches 0. Now, cosine of x times cosine of x is cosine squared. Cosine of x times positive 1. Then you have a cosine of x times negative 1. So the middle term, which we normally get when we multiply two binomials, is going to cancel because we have a sort of difference of squares pattern, or the conjugate pair of binomials. And then we have negative 1 times positive 1 is negative 1. All of that's going to be over 3 times x squared times cosine of x plus 1. No, don't worry about getting the denominator all multiplied together. It's just going to complicate things. We need that sine squared to show up. Well, 1 minus cosine squared is sine squared, so cosine squared minus 1, where the subtraction is reversed, is going to be the opposite. Why am I pointing up there? Is going to be the opposite answer. So the numerator is going to be negative sine squared. Great. We're almost done. Yeah, it's sine squared over x squared. But sine squared, excuse me, I said that wrong. Sine squared of x is 2. It's sine squared times sine squared. And in the denominator, we have an x times x. So if I just expand out these powers, I can make sine of x over x show up twice. So we're looking at the limit as x approaches 0 of negative 1/3 times sine of x over x times sine of x over x. Chalk is flying everywhere. I'm getting excited. Over 1 over. Hope I wasn't saying times when I wrote those division symbols. 1 times 1 over cosine of x plus 1. The limit as x approaches 0 of a constant function negative 1/3 is negative 1/3. The limit as x approaches 0 of sine of x over x is 1, so we have a 1 times 1. And the limit as x approaches 0 of 1 over cosine of 0 is 1, plus 1 is 1/2. And if I wasn't in my room at home with some semi-expensive chalk that I bought, I would throw it against the board like I used to in my old videos. But that is the end of my last example. That is wicked cool. All those skills we learned when doing trig proofs coming back and allowing us to analyze a limit problem based on the use of these two limit statements and getting an answer of negative 1/6. All those skills that we keep learning keep coming together, working together, and allowing us to further our knowledge through mathematics. That's quite cool. I'm Mr. True. Bam! Go to your homework.